The question that I have is, could you do an example on the calculation of the shear strength parameters from triaxial data? The question says, two samples of slightly over-consolidated clay were tested in triaxial compression and the following data at failure were obtained. So that is this right here. The pre-consolidation stress for the clay was estimated from oidometer test, which is the one-dimensional consolidation test, to be about 400 kilopascal. The question is to find the effective shear strength parameters in the normally consolidated and over-consolidated ranges. To find the shear strength parameters in the normally consolidated range, we know we have to do at least one test on a normally consolidated specimen, right? So we have the results from two tests. Can the specimens in any of these tests be considered a normally consolidated specimen? See what happened over here. Well, the soil has a pre-consolidation pressure of 400 kilopascal, right? But the test 2 was conducted with the effective cell pressure, effective confining pressure of 750 kilopascal. But the 750 is greater than 400, and therefore it might have been over-consolidated in the beginning, it doesn't matter, but it has been consolidated even higher, even to a higher pressure than that, and therefore the soil is now normally consolidated. So the specimen used in test 2 is normally consolidated specimen. On the other hand, the effective confining pressure used in test number 1 is only 75 kilopascal, which is less than 400 kilopascal. And therefore, for this test, the specimen used in this test has a pre-consolidation pressure that is higher than the actual pressure, confining pressure, that is used in the test before shearing. And therefore, this specimen is an over-consolidated specimen. So with that understanding, let's go ahead and find the effective stresses because we are interested in effective shear strength parameters. For test number 1, the total stress at failure is the cell pressure plus the deviatoric stress, sigma C prime plus sigma 1F, delta sigma 1F, and the pore pressure at failure is minus 5. We subtract that in order to get the effective stress at failure. So that works out to be 345 kilopascal. In the horizontal direction, total stress at failure is exactly equal to the cell pressure because the cell pressure remains the same, right? So therefore that's 75. And we still have to subtract the pore pressure in order to calculate the effective horizontal stress, and that works out to be 80 kilopascal. So I follow the same procedure to find the effective stresses at failure in test number 3. So here are my Mohs circles. This black circle here corresponds to test number 3, and therefore that's in the normally consolidated range. And this point right there, the one that separates the normally consolidated to over consolidated, we are going to take that as the pre-consolidation pressure, which is 400 kilopascal. This blue line here corresponds to test number 1, and therefore that's in the over consolidated range. So I have drawn the two failure lines. This red line is the failure line for the normally consolidated range, and this line right here is the failure line for the over consolidated range. So we are interested in finding the parameters defining these lines. So the slope of this red line is phi prime, and obviously there's no intercept here, and therefore C prime is 0. So these are the parameters for the normally consolidated range, and the slope of this purple line here is phi prime OC, and the intercept is C prime OC. So these are the parameters in the over consolidated range. So we just have to solve these, and the rest is therefore is simply geometry and mathematics. But I have to warn you that this is not a straightforward problem. In other words, solving this analytically is not very straightforward. But on the other hand, solving this graphically is very straightforward. So that's how we solve these problems in olden days anyway. But here, this is what you would do. You will construct this circle first, right? And then immediately you can draw the red line to be tangent to the black circle and passing through 0. Then you can measure this friction angle phi prime. So you're done with the evaluation of the shear strength parameters in the normally consolidated range because C prime is 0, right? Then what you do is you construct this blue circle, right? And then draw a vertical line at 400 kilopascal. Wherever that vertical line intersects the red line is point A. Now you draw a failure line to pass through point A and to be tangent to the blue circle. Alright, so that's your failure line in the over consolidated range. So once you have that constructed, you just have to measure the friction angle phi prime OC and the cohesion C prime OC. So that's how you do it graphically. You can see it's pretty easy to do. And if you were to solve this analytically, this is what you would do. First, we go ahead and find phi prime. Remember this equation we derived earlier, right? So we apply this to the normally consolidated range where C prime is 0 and sigma 3f prime. Obviously, we are going to use the data from test number 3. So sigma 3f prime is 300, which is equal to 1 minus sine phi prime over 1 plus sine phi prime times 920. You rearrange this in order to find your friction angle, and I get a value of 30.5 degrees from that. So that part is pretty easy. Now we come back and work on the over consolidated range. We have two parameters, C prime OC and phi prime OC, and therefore we need two equations to solve these. I apply this equation for the stresses from test number 1. I get one equation. To write down a second equation, we first recognize that this point A is on both this failure line and this failure line, right? Now that we have a value for phi prime, I can evaluate this vertical distance AB, which works out to be 235.6. Now I have the coordinates of point A. The sigma, the normal stress is 400, and the shear stress is 235.6. And I substitute the coordinates into the Mohr-Coulomb failure equation. I get a second equation. But looking at the two equations, you can see there's no direct way to solve these equations. So I've decided to solve this iteratively. So what I did was I found COC prime from equation number 2 and substituted into equation number 1. I got this equation. So now this equation is only in terms of the friction angle phi prime OC, but it's a nonlinear equation. So I call this function as y naught. Alright. Then I made a little table here. The first column is phi prime OC. Then I calculate my sine of that. So once I have the sine of that, I can calculate my Ka from this equation, right? Then I substitute everything in this expression right here in order to find the value of this right-hand side. But the right-hand side is supposed to be equal to 80, right? So I keep doing this until I get a value of 80 for y naught. So here are the three values that I tried, 20, 25 degrees, and 26 degrees, and I get these values, 43, 77, and 84. So you can see the friction angle has to be somewhere in between, so I took that as 25.5 degrees. So once you have the friction angle, you can go back to one of these equations and evaluate your C prime OC. For example, you can go back to equation number 1 and you get your value of C prime OC. I got a value of 44.8 kilopascal for that. So we are done, but you can see that solving this analytically is not that straightforward like in some of the other problems. You can do this graphically much more easily than analytically. I want to go back and make one more comment concerning the pre-consolidation pressure of 400 kilopascal. So this has to do with the differences between the loading that we apply in a one-dimensional consolidation setup and the triaxial setup. I'm out of space in this slide, so let me do it in the next slide. So during a K-node loading or one-dimensional loading, we put the soil in a cylinder and compress it vertically. So the horizontal strain is 0 because the cylinder will not allow the soil to deform in the radial direction, right? Usually we plot the results in the E versus sigma 1 prime space. So loading will follow the virgin compression line, and then the unloading, of course, will follow the swelling line, right? So the soil that we were talking about in the earlier slide had a pre-consolidation pressure of 400 kilopascal. So that means the soil had been consolidated to a pressure of 400 kilopascal sometime in the past, and then of course it might have been unloaded, right? And obviously when you take it out of the ground, you are removing the stress completely. So here is the stress path in the PQ space, right? This is the loading path, this is the unloading path. So this point A here corresponds to this point A here, and then when you take it out of the ground, you are removing the stress completely and bringing it back to zero here. You know, if I assume a K naught of 0.5 during one-dimensional loading, then I can calculate my sigma 3 from the value of sigma 1. Sigma 1 is 400. I'm talking about point A here. So sigma 3 would then be 0.5 times that. So we get 200. And I can calculate my P and Q at point A, which works out to be 267 and 200 kilopascal. Alright, so we bring the specimen to the lab and put it in a triaxial cell and consolidate it under a effective confining pressure of 750 kilopascal, right? So at the end of the consolidation phase, sigma 1 prime will be 750, sigma 3 prime will also be 750, and therefore P prime at this point is 750, Q prime is 0, right? So using this data, we are trying to figure out whether the sample is now over consolidated or normally consolidated, right? It may seem like we are comparing apples and oranges because here this is a 1D loading where the vertical stress is not equal to horizontal stress, whereas this is a isotropic consolidation where the vertical stress and the horizontal stress are equal to each other, right? In fact, it is somewhat complicated. So you have to bring in some theoretical ideas in order to actually affirmatively say that the soil is normally consolidated when you consolidate this to a confining pressure of 750 kilopascal. When the soil is consolidated to a pressure of 400 kilopascal in the field, you would have established an yield surface. So typically, the yield surface in the PQ space looks something like this. Then when you put the sample in the triaxial cell and perform an isotropic consolidation, the stress path followed is this. It goes along the p-axis, right? So from this point to this point, the state of stresses are inside the yield surface and the behavior is supposed to be purely elastic. So nothing will happen to the yield surface. Yield surface will stay wherever it is. But as soon as you go past this point, right, then the yield surface will keep expanding. So this point kind of serves like this point right here. In this space, we would say, well, you had to go past point A in order to make the soil normally consolidated, right? In other words, you load it along this line, and so once it reaches point A, then it's going to switch to the virgin compression line and goes along that line, right? So that's when it becomes a normally consolidated specimen. So a similar effect happens over here. So once you go past this point, the soil becomes normally consolidated. So from here to here, it's over consolidated. From here to here, it is normally consolidated. So in the triaxial space, you have to go past this point. But this point, the value of P at this point is not 267. It is actually higher. But since this 750 is way more than 267, right? You could safely say you would have passed this point and gone beyond, and therefore the soil can be safely assumed to be normally consolidated. I'm not questioning our assumption, but I'm pointing out how complex it is to reconcile the loading that takes place in a one-dimensional setting and the triaxial setting.